Hello, welcome to the course Electronic System Design. Last lecture we saw that we can use a simulator called SPICE to solve electrical circuits. In SPICE simulation, we make a diagram, something called schematic, where we use all the components whatever is used for electronic or electrical circuit, and then we convert that schematic into a net list which is readable by the SPICE software, and the SPICE is going to simulate and evaluate the output based on the circuit parameters. So, that was the flow actually for the SPICE, how do we solve the circuit. Now, last lecture we discussed something called operating point analysis. Operating point analysis is when we are given a circuit and we assume all the circuits, all the components are linear, time invariant, and our sources, which are voltage source or current source, they are not dynamic in nature, they are fixed value and they are not changing with time. So, operating point analysis is the steady state analysis, what will be the output of the circuit at time equal to 0. So, that is operating point analysis. After that, often we need to simulate the circuit for a complete sweep in some parameters. For example, we have a circuit, electronic circuit, and we want to see the behavior of the circuit with respect to temperature. So, temperature is a parameter which can vary within certain range. So, the output of the circuit, because the components whatever we choose, for example, the voltage source or the resistors, inductors, even active elements, so they are all dependent on the temperature and their characteristic changes with the temperature. So, often we want to find out how the output of a circuit changes with temperature. So, for that we do a separate analysis, something called DC sweep. In this DC sweep, we take a parameter and change the value from a very low value to a very high value in that given range, and we analyze the output, how does it change with that input parameter. So, for example, if we take temperature, a reasonable temperature range for an electronic circuit is minus 40 degree centigrade to 125 degree centigrade. So, all the electronic circuits whatever we see around, these are characterized only for this temperature range. Minus 40, we do not assume that our laptop will be exposed to such drastic temperature like minus 50 or minus 60 degree centigrade. So, reasonable temperature range is minus 40, and on the higher side this is 125 degrees. So, we do not assume or we do not think that our laptop will ever be exposed to higher temperatures than 125 degree centigrade. So, to check the output, how does it change with a input parameter, we use a separate analysis called the DC analysis, and that is what going to discuss today, DC sweep or the DC simulations using SPICE. So, we will discuss the DC sweep. Or we sometimes call it by dot DC statement. This is the SPICE directive or the command which we use to do the DC sweep. So, this performs a DC analysis while sweeping the DC value of an independent variable. And this variable can be voltage, current, or temperature. Etc. This analysis is also useful for computing the DC transfer function. Of a device or a circuit or plotting the current voltage characteristics. So this .dc statement is used for analyzing the circuit, and the syntax for this command is .dc. This is the statement we use to invoke the DC simulation engine, and then we have the source name, then the second parameter is V start, then third parameter is V stop, and the fourth parameter is V increment. And then there are certain other optional parameters, but these are the important parameters we have. So here we have .dc statement, which is a statement. If we write it in the netlist, then it tells Spice that to invoke the DC simulation engine so that we can solve the circuit for a DC sweep. Now, why do we want to sweep the voltage or any other parameter? To check the behavior of circuit in a changing environment. For example, as we said, the temperature is a variable which is often used for DC sweep. We want to see the characteristics or how our circuit behaves when the temperature is going from very low to a very high value. We want to evaluate the functionality of circuit for the different temperatures, so that we know how that circuit is going to behave and we can choose it or use it accordingly. This is also used for DC transfer function. For example, we have a resistor divider and both resistors are temperature dependent. So, we want to see what will be the transfer function, means the output upon the input. What is the DC transfer function look like for a given circuit. And the syntax of this DC simulation or .dc is, first we write .dc. So, .dc invokes the DC simulation engine. Then the next parameter is source name. source name is the parameter what we are going to change. For example, we want to see a circuit how it behaves when the temperature changes minus 40 to 125. So, the source name here is temperature. So, we make a variable in the netlist which is temperature, and now we write temp here or whatever is the name of that parameter we make. So, this is the source name. The next parameter is V start. So, this is the starting point of that DC parameter. It can be minus 40 or we can choose it 125 as well. Whatever is starting and stop value, we can choose V start and V stop, the next parameter. So, within that range, one is the starting value, let us say minus 40 degree, and the next is the end value which is 125 degree. We want to analyze the circuit in between this range minus 40 degree to 125 degree. Now, we do not want to use only these two parameters at minus 40 and 125. We are interested in the all the values in between. So, we want to see the circuit how it behaves at 0 degree, 1 degree, 2 degree, 3 degree. In all the temperature we want to check the performance. So, we specify a parameter which is called V increment. So, this is the increment what SPICE simulation engine is going to take while going from V start to V stop. So, for example, minus 40 is the starting point and we choose V increment as 1 degree. So, SPICE simulates the circuit at minus 40 degree and the next at minus 39 degree, then minus 38, and this is how it increases to 0 degree, then 1 degree, 2 degree, 3 degree. So, the increment in between these two temperature value is 1 degree, which we can specify here. So, in DC sweep we are very much interested in very small steps, so that we know exactly how the circuit is going to behave for a very small change in the temperature. However, we cannot use V increment very small, because then for each and every increment SPICE is need to solve all the circuit altogether. So, our computational time increases if we increase V increment is very small value. So, we put it reasonable so that the computation time is within the limits and we analyze the circuit accordingly. So, V increment is generally a parameter which we choose very wisely in going from V start to V stop, so that we do not miss out on any particular value. For example, if our circuit is very sensitive to temperature at 0 degree, so instead of simulating minus 40 to 125, we simulate the circuit only between, let us say, minus 5 to 5 degree with a very finer V increment, very small V increment, so that we do not miss out any abnormality in the circuit. This particularly happens in case of active circuits, not with resistor and inductor. If we have MOSFETs and semiconductor devices, these devices are very sensitive to temperature or even other parameters. So, there we need to find V increment very carefully, so that we do not miss out on any particular type of behavior. So, this is how we simulate using .dc statement. So, this is the DC sweep. So, the same thing we can write for temperature. For temperature we have separately a syntax. So, DC sweep under various junction temperature syntax is dot temp this is T1 T2 and so on. So the same statement we can use because temperature is the parameter which we choose very often. So there is a separate command itself for DC sweep of temperature dot temp, and this is equivalent to, you can write dot step temperature, and we can provide a list at what temperature we want to solve the circuit. So this is temperature 1, let's say -40, this is temperature 2, this is 125 and so on. So this is kind of simulations we can do using DC sweep. So there is a separate statement .dc where we can specify any parameter. It can be voltage, current, even width, length, all other parameters, whatever we choose in the circuit. .dc is a general statement for any parameter. However, for the temperature we have special statement .temp. If we use .temp, this is also does the SPICE DC simulation for temperature T1, T2, T3, and we can specify number of temperatures. So this is how we do the DC simulation using SPICE. Now let's see how we do it in the LT SPICE simulation software. So when we open the SPICE, it looks something like this. We go to the new schematic, and here let's create a very small schematic which is a temperature dependent simulation. So we use ground first, we take a voltage source, we connect this voltage source, let's say this DC voltage is, for example, 0 for time being. We will change it. We take a diode D1, and this diode we have to choose from new model. So here one thing to note is when we take the element from the top, this top panel, these are ideal diodes, so they do not have many parameters to change. But if we do right click on it and this dialog box open, we can pick new diode. From here we can pick a realistic diode. For example, let's say we take this 1N5817, which is a Schottky diode manufactured by Yon Semi company. So if we take this diode is having temperature dependent characteristics because this is a real diode. Let's use this. We connect this. So this is the complete circuit. Now let's write the DC statements. We go to this configure analysis, we do the DC sweep. So here if we click the DC sweep, the first thing we need to notice is there are three sources, first source, second source and third source. So we can simultaneously sweep three sources in a single simulation. So we are going to use only one sweep. So let's go to first source and name of the first source to sweep. We want to sweep the voltage V1 across this diode. So we write here V1. The type of sweep is we are going to use linear. So we want to linearly increment it. Let's say the start value is 0. We want to sweep from 0 to, let's say 2 volt. So stop value is 2 volt and the increment is 0.01. So by this configuration we are telling SPICE that V1 is the voltage source which is going to change linearly from 0 volt to 2 volt with the increment of 0.01. So first simulation will be at 0 volt, the next simulation will be at 0 plus 0.01, which is 0.01, then next simulation is 0.02, then 0.03, then 0.04 and so on. So we can have like hundreds of simulation by specifying these values. We specify this. So this is the DC sweep we are going to use, and let's say we want to change the temperature as well in the same simulation. So let's say we have the temperature simulation. So we uses spice directive, which is dot temp, and temperature I want to use is -40, 25 and 125. These are very commonly used three temperatures. 25° is used for the room temperature, how the circuit behaves at room temperature or the normal temperature. -40 is the colder extreme, so how the circuit behaves at -40°, and 125 is the on the other extreme where circuit is very exposed to very hot conditions, so that is 125. So let's use this statement as well. So now we have this circuit ready. This voltage source is going to sweep from 0 to 2 volt, and this diode is connected to this voltage source. So it means we are going to change the voltage across this diode from 0 to 2 volt, and we want to analyze this analysis for 3 different temperature: -40, 25 and 125°. So let's simulate this circuit and see how the result comes out. So when we simulate it by this green color symbol, we see on the x-axis, which is the sweep parameter. In this case is V1, which is 0 to 2 volt. So here you can already see the x-axis is changed from 0 to 2 volt, which is your diode voltage. Now let's add the trace here by right clicking here and then add trace. If we select the drain, the diode current, which is ID1, we select it and do OK. So now you see we have 3 graphs here. So why do we have these 3 graphs? Because we have the same analysis for 3 different temperatures. One is at -40, one is 125 and one is 125 and 25. So this is how we see the characteristic of diode. If we just see this thing, this looks better. Here we have this circuit and these are the diode characteristic at 3 different temperature. So this is how we analyze the circuit. Now very often we want to analyze these results using some external softwares as well. For example, we have got these ID VD characteristics. Now I want to export this data into Excel sheet, Microsoft Excel sheet or some other software and analyze there. Instead of I want to analyze here I can zoom in, zoom out, but I want to perform certain other calculations on this data. So how to port this data to some external software? So this is how you can do that. You go to this trace and do the right click here. If you do the right click, there is an option on the bottom which is file. You go to file and export data as text. If you do this, export data as text, this is the default location. You can change it to any other location, for example desktop. And if you open this text file which you just saved, this is how the data look like. The first parameter is the step value where the voltage is changing first from 0 to 0.00, 0.01, 0.02, 0.03, and accordingly what is the value of diode current. This is the y axis is the current which was plotted in this figure, and this first list is for temperature equal to -40. So, that at -40 temperature, these are the values diode voltage and diode current. If you go down here, these are the same value, these are the values for temperature 25. The diode current is different, step will be same, and if you go little lower, you see the temperature is 125 here, and you get the data x in the xy format for all these traces. So, this is how you can analyze the circuit and export the data into a text file which you can use later on in any other softwares. So, this is how you perform the DC sweep. Now, when we do this DC sweep, we go from a starting point to a ending point in some increments, let us say 0.01, 0.02. So, for the present example, we use the sweep type as linear, where we are going from 0 to from a low value to a high value in a linear increment, 0.01 in the next 0.01, next 0.01. This is how we are simulating. So, this is called the linear sweep or linear type of DC sweep, where we go linearly. However, for semiconductor devices, many of the characteristics of circuit are not linear with the parameters. For example, if we talk about the drain current of a MOSFET, we want to plot it with respect to the gate voltage, but for the sub-threshold slope, the characteristic is logarithmic, it is not a linear characteristic. We want to see the sub-threshold region in the logarithmic scale. So, I do not want to do a linear sweep from low value to high value, because linear sweep is going to do so many simulations even in smaller range. However, I am more interested in the logarithmic scale, where the first step is very big, then we have very small step, very small. So, this is how we want to do the simulation. So, we have actually 4 types of DC sweep which we can specify. Instead of linear sweep, we can just drop down in that example where we choose linear sweep. There are some other 3 types of sweep which we can use to simulate our circuit. So, we have actually 4 types of DC sweeps in our SPICE software. So, we have 4 types of DC sweep. So, the first one is the linear sweep. And in this linear sweep, we have equal intervals defined by the increment. The second one is called octave. In this type of DC sweep, we do simulations every 2 times. So, number of octaves equal to logarithm at the base 2 stop value divided by the start value. In the third type, we have decade. So the every simulation is done 10 times for a decade. So the number of decades is similar formula, but now log is at the base 10 instead of 2. So log at the base 10 stop value divided by start value. And the fourth one is list type of sweep. So in this type of sweep, we specify the individual values. So we have these four types of sweep. In the linear sweep, we do specify an increment, let's say 0.1. So the parameter is going to change, let's say 0 to 10 in a step of 0.1. So 0, 0.1, 0.2, 0.3, 0.4. This is how we simulate. Next is the octave. So that simulation is done every 2 times. So number of octave is log at the base 2 stop value over the start value. Decade is every 10 times in a decade. So number of decades, number of simulation points will be log at the base 10 stop value divided by the start value. The fourth type is list, where we are interested only in particular values. For example, in the last example, we sweep the temperature only for 3 values, which is -40, 25 and 125. So that is kind of a list type of DC sweep, where we specify only these 3 values. However, we can do that by a linear sweep also, where we specify -40 and 125 with a step of 10 degree. So their simulation will be -40, -30, -20, -10, 0, 10, 20, like this. So, but temperature generally we are more concerned only in these 3 extremes. What is the room temperature performance, what is the on the extreme colder situation or extreme hot situations. So, we specify the values only for these 3 values for temperature. So, these are 4 types of sweep we perform. Now, let us see how do we import some other models into SPICE. So, why do we do it? So, for example, we use the SPICE, this LT SPICE, which has a very big library. Library means we have set of models for many components. For example, we go to market, buy a linear technology diode. So, that diode model will be already there in our LT SPICE. We can take this, we can make the circuit, we can same circuit we can do in this, we can make a schematic in LT SPICE and simulate it, see the performance. Often a time when we go to market, we are not limited only to buy a particular manufacturer's product only. There are so many semiconductor devices manufactured by so many companies. So, how I can simulate the circuit from all of these vendors. So, one way is all these manufacturers, when they make these devices, they also provide a spice model for those elements. Let us say I go to a market, buy a diode from some company, let us say Analog Device. So, on Analog Device website, I can go and use the model of this diode in LT Spice itself. We can import that spice model in LT Spice, and then I can use that model to simulate my circuit using this analog device components. So, all the devices what is available on the market, they come up with the spice model also, which we can import to LT Spice, and we can use any component in our circuit design. So, how do we import the third party model? This is called the third party model, where we have spice which is our own LT Spice, and I want to use any arbitrary component from the market which the model is available. So, how to import this third party model into LT Spice? So, this is what we are going to discuss. So, now there are statements in spice where we can tell the spice or LT Spice that I am going to use a third party model. So, there is a proper statement or spice directive for that, that is called dot model or dot sub circuit. These are the spice directives. When we write it in the schematic, it tells the spice that for this component I am going to use a third party component and take the model from that respective location. So, this is how with these these two statements we tell spice to use a third party model. And there are four methods actually to do the same job. One is we can directly copy and paste that model into our spice netlist or spice schematic. That is one way, simple copy and paste. Second is we can use dot include. It is like including a separate file in your spice simulation, and that file contains the model of that component. The third one is we are using .lib, which is a library file. Library file contains all the circuits, whatever circuit or model that library has. And the fourth one is we can directly link our circuit simulation to a external website where this model is present. We can, just like we search on Google, we can search using the URL on the browser. The same URL we can specify in the schematic, and when we simulate this circuit, automatically spice will look over the internet and find out the model on that path which we have given and take the spice model directly from that. The limitation of this this method is when you are doing the simulation, your computer should be connected to internet, otherwise it will not be able to fetch that model. So, these are the four models or four methods which we use to import the external third party circuit into our simulation. So, let us write it down. How to import third party models into LT Spice. So, two types of statement we can use. The first one is dot model. This is used to include intrinsic spice devices like diodes and transistors. And the second type of statement is dot subcircuit. Dot subckt. So this can include the collection of circuitry. So here in dot model, we can include a single device, for example, a single diode or a single transistor. However, in dot subcircuit, if we have, let's say, a small circuit made up of two diodes, resistors, capacitors, or any other devices, so that is included using dot subcircuit. It can have multiple devices as well. And there are now there are four methods to do the same thing. The first one is copy and paste. Second method is use dot include. Or in short, we can write dot inc. This is the statement. The third is use dot lib. And the fourth one is use URL. This is the link over internet. So these are the four methods. We have method 1, copy and paste the complete model in the schematic itself. In this case, our schematic will be complete in itself. If we have a single schematic and everything, all the models are specified in the schematic itself, we can use the same file to simulate at the other machine itself without worrying of copying other library files or any other thing. because the schematic is complete in itself. However, in .include and .lib, this schematic is calling a separate file from the background from the same directory or so and simulating with our present circuit. In this case, when we copy this schematic file, we also need to copy the attached library files also in the same directory if we want to port this simulation into some other machine. So, that is the limitation, but if we have so many third party devices, then it is not possible to all copy and paste in the same schematic. The space wise will not be a very good idea. So, in that case, if we have so many third party models, then we use .libs and .include. The fourth is URL. We just specify the URL and machine is going to import the data or import the model from over the internet, but during the simulation your internet connection should be active. So, that is the limitation. Personally, I do not like URL method because the models can change over the time dynamically and we may not be knowing that the manufacturer has changed and our circuit is behaving differently. So, the first copy and paste is not very good method if we have, let us say, 10 third party components. So, 10 models we have to copy and paste, it looks very clumsy. So, .include method is very much used by circuit designers, .include and .lib. So, these are the four methods of importing a third party model. Let us see in the LT Spice how do we import this kind of model into LT Spice. So, we go to new schematic and we make a simple circuit. Let us say we have ground connection, we take voltage source, value is 0 volt and we connect this a diode. Now, this diode I want to change with a third party model. So, I do a right click. First I want to see whether my diode is already available in LT Spice or not. So, I click on pick new diode and these are all the diodes which are available from all these manufacturers like Silicon, Schottky. These are manufacturers, onsemi, Vishay. These are all the companies which are making these diodes. Let us say I choose a diode which is not available in this list. So, for example, I go to a very general diode which is 1N4001G. So, this diode is very much used, but this is not available in this list. So, I cannot choose that diode here. I need to go to third party website, which is this diode is made up by diode. So, how do I import that model here? I go to the internet and find out the model for this 1N4001G. So, I go to Google and search for this diode. This link will come up and if I press on this link, this goes to this page. This is the manufacturer of this diode, and if we go below, we have the Spice model available here. If we see this, we have this Spice model available for this diode 1N4001G. So this is the model for this diode. We can save this as per our requirement. We can, in the same directory, we need to use it. This SPICE model, if we open up in the notepad, we see this is the diode manufacturer's comment, and we see there is a statement dot model here. So this is the SPICE model for this particular diode 1N4001G, and the name of this component is given as DI_1N4001G. So let's perform the first method where we copy the model completely into the schematic itself. So we select this complete model and copy it, and we can paste it over here itself. So this is the model we have written here, and now we need to go to this diode. We want to map this diode to this model. So we go on this diode, make it control and right click at the diode. So we press the control key and then right click, then we open up this component attribute editor, and here we can replace the value by this name, which is DI underscore 1N4001G. So this is the name of this component. After this dot model statement DI, we do it OK, and then we can use this model of this diode here. If we click it, this is going to simulate it. Let's say we do a DC sweep. The voltage source is V1. Type of sweep, we want to go linear. Start value is 0, stop value is 2, and increment is 0.01. So here it's able to simulate it. Let's add traces, which is diode current. So this is the diode characteristic of a diode 1N4001G, which is a third party diode which is not already available in the LT SPICE, but when you go to market and buy this diode, this comes with a SPICE model which you can download from diode website, which we just saw, and using that dot model statement we can simulate this device. However, if we don't have this dot model statement, let's say we right click on it and we don't include this dot model statement here, it means we do not have now the dot model for this diode, then LT SPICE is not going to simulate. It is going to say that you cannot find the definition of dot model. So this is how we include these statements, and we can include a new model in our LT SPICE simulation. So in today's lecture we saw that we have multiple type of DC sweeps where we can change the value from very low value to a very high value, and we also saw that if we are using a third party component, how to include that circuit into our LT Spice, we go to that manufacturer of that website and find out the model which is generally available on manufacturer's website. For that particular component, we search the Spice model which is suitable for our simulation. For LT Spice, Spice 3 model is compatible with our LT Spice software. We go to manufacturer website, download that model, and we can copy and paste, or there are some other 3 different methods to include that component. So, this is what we saw. We copy the dot model statement into our schematic and change the attribute of our normal diode to a realistic diode which is made by the manufacturer. So, this is how we include third party components in our circuits. So, this is all for today. Thank you.